Imagine you are the fastest thing that has ever existed in this universe. You are light itself. You move at 300,000 kilometers every single second. Nothing in the known laws of physics can ever move faster than you. You are the absolute ultimate speed limit of reality. Now imagine you pick a direction, any direction. It does not matter which one, up, down, left, right, towards some distant galaxy glowing faintly in the cosmic dark. You start moving. You move at full speed. You never slow down. You never stop. You travel for 1 year, then 10 years, then 1,000 years, then 1,000,000 years, then 1,000,000,000 years. You keep going and going and going. You cross unimaginable distances. You pass through voids so empty that not a single atom exists for millions of light years in any direction. You pass through galaxy clusters, through filaments of cosmic structure, through regions of space so vast that the human mind cannot even begin to comprehend them. And yet, after all that travel, after billions upon billions of years of moving at the fastest possible speed that physics allows, there are places in this universe that you will never reach. Ever. Not in 1,000,000,000 years. Not in 1,000,000,000,000 years. Not in an infinite amount of time. They are gone. They are beyond your reach forever. And they are getting more unreachable with every passing second. Now let that sink in for a moment. You are light, the fastest thing in existence. And there are places you cannot go. There are regions of this universe that are permanently, fundamentally, absolutely cut off from you. Not because there is a wall in the way. Not because there is some physical barrier blocking your path. Not because you lack the energy or the technology or the fuel. But because the very fabric of space and time, the very structure of reality itself, makes it impossible. The universe has a boundary. Not a boundary made of matter. Not a boundary you can touch or see or break through. But a boundary that is more absolute, more unbreakable, more final than any wall ever built by any civilization in the history of existence. And you are inside it. Right now, reading these words. Trapped, permanently, inescapably, you are inside the observable universe. And the observable universe is a prison you can never escape. Now I know what you are thinking. That sounds dramatic. That sounds like science fiction. That sounds like something a philosopher would say late at night after reading too many books about cosmology. But here is the thing. This is not philosophy. This is not science fiction. This is not speculation or theory or hypothesis. This is hard, measured, confirmed, peer-reviewed, Nobel Prize-winning physics. This is what the data tells us. This is what the mathematics proves. This is what every observation we have ever made about the large-scale structure of the universe confirms beyond any reasonable doubt. We live in a finite bubble of accessible reality, and that bubble has walls, and those walls are getting farther away from us in terms of what we can see from the past, but they are getting closer to us in terms of what we can reach in the future. We are on a shrinking island of causal influence, and the ocean around us is growing without limit. Before we dive into the depths of this topic, before we explore exactly how this prison was built, who the guards are, what the walls are made of, and whether there is any possible way out, I need to share with you a piece of scientific history. A real story. A story about real scientists doing real measurements that changed everything we thought we knew about our place in the cosmos. The year was 1998. Two teams of astronomers were working independently on what they thought would be a straightforward measurement. The Supernova Cosmology Project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory, and the High Z Supernova Search Team, led by Brian Schmidt at Mount Stromlo Observatory in Australia, with Adam Ries performing the key data analysis. Both teams were trying to answer what seemed like a simple question. We know the universe is expanding. Edwin Hubble proved that back in 1929. but the expansion should be slowing down. Right? Gravity is attractive. All the matter in the universe is pulling on all the other matter. So the expansion that started with the Big Bang should be gradually decelerating. Like a ball thrown upward, eventually slowing, maybe even falling back. The question was simply, how fast is it decelerating? By measuring how fast the expansion is slowing, you can predict the future of the universe. Will it expand forever, but slower and slower? Will it eventually stop and collapse back in on itself in a big crunch? The answer matters. It determines the fate of everything. To make this measurement, both teams used a particular type of stellar explosion called a Type 1 supernova. These explosions are special because they all have roughly the same intrinsic brightness. They are what astronomers call standard candles. If you know how bright something truly is, and you measure how bright it appears from Earth, you can calculate how far away it is. Simple geometry of light. So both teams found dozens of these Type 1 supernovae in distant galaxies. They measured their apparent brightness. They calculated their distances. They measured the redshift of their host galaxies to determine how fast those galaxies are receding from us. And then they compared the distance measurements to the recession speeds to figure out how the expansion rate has changed over cosmic time. The expected result was clear. The expansion should be decelerating. Every textbook said so. Every theoretical model predicted it. The only question was, how much deceleration? Was it a lot? A little? Enough to eventually reverse the expansion? The actual result was something nobody expected. The expansion was not decelerating at all. It was accelerating. The universe was not slowing down. It was speeding up. Distant supernovae were farther away than they should have been. The expansion had not been putting on the brakes. It had been stepping on the gas. And it had been doing so for billions of years. Both teams got the same result. Independently, using different supernovae, different telescopes, different analysis methods. The result was real. The universe is not just expanding. It is expanding faster and faster and faster. Something is pushing it apart. Something is adding energy to the expansion. Something is accelerating the growth of space itself. And whatever that something is, it had just locked the door of our cosmic prison and thrown away the key. This discovery earned Perlmutter, Schmidt, and Ries the Nobel Prize in Physics in 2011. It was described as one of the most important discoveries in the history of cosmology. And its implications are staggering. Because if the expansion is accelerating, then there are galaxies we can see right now whose light will never reach a future observer. There are objects in our sky tonight that are already lost to us. The universe is not just big, it is actively, continuously, relentlessly removing itself from our reach. And that is what this video is about. The most profound, the most disturbing, and yet the most scientifically fascinating realization in modern cosmology. We are prisoners, not of walls or chains or bars, but of space-time itself, of the very geometry of existence. And there is no escape. Now, if this kind of deep scientific exploration of the universe fascinates you, if you want to understand reality at its most fundamental level, if you want your mind genuinely expanded by real physics rather than speculation and fiction, then you are in exactly the right place. Hit that subscribe button right now. Turn on notifications. Because on this channel we go deeper than anyone else. We do not just tell you facts. We explain the why. We explain the how. We trace the logic from first principles to final conclusions. And this video in particular is going to take you on a journey through physics, through cosmology, through quantum mechanics, through the mathematics of space-time, through every angle of this question. It is going to be long. It is going to be detailed. It is going to be thorough. And by the end of it, you will understand the universe in a way that very few people on this planet truly do. So like this video right now to help the algorithm share this knowledge with others who are curious. Drop a comment telling me whether you think we will ever escape this cosmic prison. I want to know your thoughts. I read every single comment. And let us begin. To understand why the observable universe is a prison, we first need to understand what the observable universe actually is. And this requires us to make a very important distinction. A distinction that most people, even many science enthusiasts, do not fully appreciate. The distinction between the universe and the observable universe. The universe is everything. All of space, all of time, all of matter and energy. Every particle, every field, every quantum of existence. The universe is the totality of reality. It may be infinite. It may be finite, but unbounded, like the surface of a sphere but in higher dimensions. We do not know its true size. We may never know. It could extend forever in all directions. It could wrap around on itself in some topology we cannot directly perceive. What we do know is that it is vastly, incomprehensibly larger than what we can observe. The observable universe is something much more limited. It is the spherical region of the universe from which light has had time to reach us since the beginning of cosmic time. The universe is approximately 13.8 billion years old. Light travels at a finite speed. Therefore, there is a maximum distance from which light could have traveled to us in that time. You might think that distance would be 13.8 billion light-years. After all, if light has been traveling for 13.8 billion years, it should have covered 13.8 billion light-years of distance. But you would be wrong. And the reason you would be wrong is one of the key ingredients of our cosmic prison. The actual radius of the observable universe is not 13.8 billion light-years. It is 46.1 billion light-years, more than 3 times what you might naively expect. How is this possible? How can we see something that is 46 billion light-years away if the universe has only existed for 13.8 billion years? The answer is expansion. While light was traveling toward us from those distant objects, the space between us and those objects was expanding. The objects were being carried farther away even as their light was making its way to us. So by the time their ancient light finally arrives at our telescopes, the objects themselves have been carried much farther away than the distance the light actually traveled. This is called the comoving distance. It is the distance to an object right now, accounting for all the expansion that has occurred during the light's journey. So the observable universe is a sphere centered on us, with a radius of 46.1 billion light-years. Its diameter is about 93 billion light-years. And within this sphere, we can see approximately 2 trillion galaxies. Each galaxy contains hundreds of billions of stars. Each star potentially hosts planets. The numbers are staggering. The observable universe contains something like 10 to the power of 80 atoms. It is unimaginably vast and complex and rich. And yet, it is a tiny fraction of the whole. The observable universe is not the universe. It is just the part we have access to. The rest exists. Physics tells us it must exist. The cosmic microwave background radiation shows us that space extends far beyond what we can see, with the same properties, the same density, the same physics, presumably the same galaxies and stars and planets, and perhaps even life. Studies using the Planck satellite data and geometric arguments suggest that the total universe is at least 250 times larger in volume than the observable universe. And it could easily be infinite. All of that is out there, right now, existing, real, full of stars and galaxies and perhaps civilizations. and we cannot access any of it. We cannot see it. We cannot signal it. We cannot know anything about it directly. We are cut off, isolated, confined to our little bubble, our 93 billion light-year wide bubble, which sounds enormous, and it is. But compared to the whole, it is nothing. A grain of sand on an infinite beach, a drop of water in a limitless ocean. That is the first layer of our imprisonment. We can only observe a fraction of what exists. But it gets much worse than this. Because the boundary of what we can observe is actually not the most important boundary. The most important boundary is the boundary of what we can reach. And that boundary is much, much smaller. And it is shrinking. To understand this, we need to go deeper into the expansion of the universe. We need to understand not just that the universe is expanding, but how it is expanding, why it is expanding, and what that expansion actually means in physical terms. When we say the universe is expanding, we do not mean that galaxies are flying outward through space like shrapnel from an explosion. This is a very common misconception. The Big Bang was not an explosion in space. It was not an event that happened at some specific location with matter flying outward into a pre-existing void. There is no center of the expansion. There is no edge. There is no point from which everything is moving away. What is actually happening is far stranger and far more profound. Space itself is growing. The fabric of space-time, the very arena in which everything exists, is stretching. It is not that galaxies are moving through space away from us. It is that the space between us and those galaxies is growing. New space is being created, everywhere, at every point, uniformly, and as new space appears between objects, those objects are carried apart. Not because they are moving, but because the ground beneath them is stretching. Think of it like this. Imagine you have an infinite rubber sheet. On that sheet, there are dots drawn at regular intervals. These dots represent galaxies. Now imagine the rubber sheet is being uniformly stretched in all directions. Every point on the sheet is moving away from every other point. There is no center of the stretching. Every dot sees every other dot moving away. The farther apart two dots are, the faster they appear to recede from each other. Not because the dots are moving faster, but because there is more stretching rubber between them. This is Hubble's law. The recession velocity of a galaxy is proportional to its distance from us. Mathematically, v equals h0 times d. Where v is the recession velocity, d is the distance. And h0 is the Hubble constant, which measures the current rate of expansion. The current best estimates put the Hubble constant at somewhere between 67 and 73 kilometers per second per megaparsec. That means for every megaparsec of distance, about 3.26 million light-years, a galaxy is receding from us at an additional 67 to 73 kilometers per second. Now here is where things get interesting and terrifying. If recession velocity increases with distance, then at some sufficiently large distance, the recession velocity must equal the speed of light. And at distances greater than that, the recession velocity exceeds the speed of light. Galaxies beyond a certain distance are moving away from us faster than light. Wait, stop. Does that not violate Einstein's special relativity? Does that not violate the fundamental law that nothing can travel faster than light? No, it does not. And understanding why it does not is absolutely critical to understanding our cosmic prison. Einstein's special relativity says that nothing can travel through space faster than light. No object, no signal, no information can move through the fabric of space-time at a speed exceeding 300,000 kilometers per second. This is an absolute law. It has been tested to extraordinary precision. It is never violated. But here is the key distinction. The expansion of space is not travel through space. Galaxies that are receding from us faster than light are not moving through space at superluminal speeds. They are essentially stationary in their local region of space. It is the space between us that is growing. And there is no law in physics that limits how fast space itself can grow. Space is not a thing that moves. It is the stage on which things move. And the stage can stretch at any rate whatsoever. This is a prediction of Einstein's general relativity, and it is confirmed by observation. We can see galaxies that are currently receding from us faster than light. Their ancient light, emitted long ago when they were closer and receding more slowly, has reached us. But the galaxies themselves, right now, at this moment, are moving away from us at speeds exceeding the speed of light. And we can never catch them. We can never reach them. We can never send them a signal that will arrive. They are lost. The distance at which recession velocity equals the speed of light is called the Hubble radius, or the Hubble sphere. It is currently about 14.4 billion light-years away from us in every direction. Everything beyond this distance is receding superluminally. And you might think this is the boundary of our prison. But it is actually more subtle than that. The true boundary, the real wall of our prison, is something called the cosmic event horizon. And it is even more oppressive than the Hubble sphere. To understand the cosmic event horizon, we need to think carefully about what it means to send a signal into the future. Imagine you emit a photon of light right now. That photon heads out into the universe at the speed of light, 300,000 kilometers per second. Unstoppable, tireless, but as it travels, the space it is traveling through is expanding. The photon is trying to reach a distant galaxy, but the space between the photon and that galaxy is growing. It is like trying to walk to the end of a corridor that is stretching faster than you can walk. If the expansion of space between the photon and its target is growing at exactly the speed of light, the photon makes no progress. It runs forever, but gets no closer. If the expansion is growing faster than the speed of light, the photon actually loses ground. It is moving forward at maximum possible speed, but the distance to its target is increasing even faster. It will never arrive. Never, not in an infinite amount of time. The cosmic event horizon is the boundary beyond which this is the case. It is the maximum distance to which we could ever send a signal, even if we send it right now, even if we wait forever for it to arrive. Objects beyond the cosmic event horizon are permanently, irrevocably out of our causal reach. We cannot influence them. We cannot communicate with them. We cannot interact with them in any way. They might as well not exist as far as our physics is concerned. The current cosmic event horizon is at a comoving distance of approximately 16 to 17 billion light-years from us. That is significantly smaller than the 46 billion light-year radius of the observable universe. Think about what this means. There are objects we can see, right now, tonight, through our telescopes, that we can never reach. We can observe their ancient light. We can study them. We can learn about them. But we can never visit them, never signal them, never touch them. They are visible but untouchable. Like a prisoner looking through a window at a world they can never enter. And it gets worse. The cosmic event horizon is not static. Because the expansion is accelerating, the event horizon is getting closer to us in terms of comoving distance. More and more galaxies are crossing beyond it every moment. Right now, at this very second as you are listening to these words, approximately 20,000 galaxies are crossing our cosmic event horizon. 20,000 galaxies, disappearing from our accessible universe. Forever their light will continue to reach us for a while, increasingly redshifted, increasingly faint, increasingly stretched, but eventually, even their light will fade to nothing. and they will be gone. Completely, permanently, as if they never existed. This is not some far future scenario. This is happening right now. It has been happening for billions of years. And it will continue happening, faster and faster, forever. The accelerating expansion is continuously removing objects from our accessible universe. Our island of influence is shrinking. The ocean of unreachable space is growing. We are on a raft in a flood that will never end. And the waters are rising. Now, let us go even deeper. Let us understand the geometry of this prison in a more rigorous way. In physics, we use a concept called a light cone to describe the causal structure of spacetime. Your past light cone is the set of all events in spacetime that could have sent a signal to you, traveling at the speed of light or slower, that has already arrived. It represents all the events that could have influenced your present state. Your future light cone is the set of all events in spacetime that you could influence from your current position by sending a signal at the speed of light or slower. It represents all the events you could potentially affect in flat, non-expanding spacetime, like the spacetime of special relativity. Your past and future light cones are symmetric. The set of events that could have influenced you is a mirror image of the set of events you could influence. Past and future are balanced. But in our expanding universe with dark energy, this symmetry is dramatically broken. Your past light cone is large. It extends back to the Big Bang. It encompasses the entire observable universe, all 93 billion light-years of it in diameter. That is the set of events that have influenced you or could have influenced you. But your future light cone is much, much smaller. It extends only out to the cosmic event horizon, about 16 to 17 billion light-years in comoving distance. And it is getting smaller. This asymmetry is the mathematical expression of our imprisonment. We can know about far more of the universe than we can ever influence. Our knowledge outstrips our power. We can see the prison from inside. We can map its extent. We can measure its walls. But we cannot reach beyond them. There is a beautiful and terrifying way to visualize this using what physicists call conformal diagrams or Penrose diagrams, named after the mathematician Roger Penrose. In these diagrams, space-time is compressed and distorted so that the entire history and future of the universe fits in a finite picture, with light always traveling at 45-degree angles. In such a diagram, you can clearly see how the future light cone of any observer in our universe terminates at a boundary. Beyond that boundary lies space-time that is causally disconnected from us forever. It exists. It is real. But it is not ours to access. Let us talk about the force that maintains this prison. The guard, if you will. The entity responsible for the acceleration of the expansion that makes our cosmic event horizon a permanent, unbreakable barrier. This force is called dark energy, and it is one of the deepest mysteries in all of physics. Dark energy is the name we give to whatever is causing the expansion of the universe to accelerate. We call it dark because we cannot see it directly. It does not emit light. It does not absorb light. It does not interact with ordinary matter in any way that we can directly detect. We only know it exists because of its gravitational effect on the expansion of the universe. And yet, despite being invisible and undetectable through any direct means, it constitutes approximately 68% of the total energy content of the universe. 68%. More than 2/3 of everything that exists in terms of energy is this mysterious, invisible, repulsive force that we barely understand. Ordinary matter, the stuff you and I are made of, the atoms and molecules and particles that make up stars and planets and people, constitutes only about 5% of the universe's energy budget. Dark matter, which is a different mystery entirely, makes up about 27%, and dark energy makes up the remaining 68%. We are a 5% minority in a universe dominated by something we cannot see, cannot touch, cannot detect directly, and do not understand. And that something is our jailer. What do we know about dark energy? We know several important things. First, it has negative pressure. In general relativity, both energy density and pressure contribute to gravity. Positive pressure, like the pressure inside a star, actually increases gravitational attraction. But negative pressure does the opposite. It creates a repulsive gravitational effect. Dark energy has such strong negative pressure that its repulsive gravitational effect overwhelms its attractive effect from its energy density. The net result is anti-gravity. Cosmic repulsion, a force that pushes everything apart. Second, dark energy appears to have a constant energy density. As the universe expands and space gets bigger, the amount of dark energy per cubic meter of space stays the same. This is radically different from matter and radiation. If you take a box and make it bigger, the matter inside gets more dilute, its density decreases. The same with radiation. But dark energy does not dilute. More space means more dark energy. This creates a terrible positive feedback loop. The expansion creates more space. More space contains more dark energy. More dark energy drives faster expansion. Faster expansion creates even more space. And on, without limit. Third, dark energy appears to be uniform. It is the same everywhere. It does not clump or cluster. It is smooth throughout all of space, at every point in every direction. This uniformity means there is no escaping it. No matter where you go in the universe, dark energy is there, pushing space apart at the same rate. There is no region of space where it is absent. There is no safe haven. There is no refuge. The simplest theoretical explanation for dark energy is something called the cosmological constant, represented by the Greek letter lambda. This was originally introduced by Albert Einstein in 1917, just 2 years after he published his general theory of relativity. Einstein added the cosmological constant to his field equations of gravity in order to keep the universe static. At that time, everyone believed the universe was eternal and unchanging. Einstein needed a repulsive force to counterbalance gravity and prevent the universe from collapsing. So he added lambda, a constant energy density permeating all of space, providing just enough repulsion to balance gravitational attraction. Then in 1929, Edwin Hubble discovered that the universe is expanding. Einstein no longer needed the cosmological constant. He reportedly called it his greatest blunder and removed it from his equations. But now, 7 decades later, the cosmological constant is back. With a vengeance. The accelerating expansion discovered in 1998 is perfectly consistent with a cosmological constant. A constant, uniform energy density filling all of space, providing a repulsive gravitational force. Einstein's blunder turns out to have been his most prescient insight. But what is the cosmological constant? What is this energy that fills empty space? The most natural interpretation from particle physics is that it is the energy of the quantum vacuum. In quantum mechanics, empty space is not truly empty. It seethes with virtual particles popping in and out of existence, with quantum fluctuations in every field. These fluctuations carry energy, and this energy should contribute to the cosmological constant. The problem is that when you calculate how much energy the quantum vacuum should have, based on quantum field theory, you get an answer that is absolutely insane. The calculated value is larger than the observed value by a factor of 10 to the power of 120. That is a 1 followed by 120 zeros. This is sometimes called the worst prediction in the history of physics. The cosmological constant problem. We know dark energy exists. We know how much of it there is. But our best theory for what it should be is wrong by 120 orders of magnitude. This is not a small discrepancy. This is a failure of our understanding of truly epic proportions. And yet, despite not understanding what dark energy is, we can measure what it does with extraordinary precision. We know it is there. We know its effects. We know it is accelerating the expansion. And we know that as long as it persists, our cosmic prison is permanent and inescapable. There is another important thing to discuss about dark energy. Recent observations from the Dark Energy Spectroscopic Instrument, known as DESI, which released its first major results in April 2024, have hinted at something remarkable. The data suggest that dark energy might not be perfectly constant. It might be changing slightly over time. Specifically, the data hint that dark energy might have been slightly stronger in the past and is now slightly weakening. This is extremely preliminary. The statistical significance is not yet conclusive. Much more data is needed. But if this turns out to be true, it would be revolutionary. It would mean that dark energy is not the cosmological constant. It would be something dynamic, something that evolves, and, in principle, something that could potentially weaken further in the future. Could it weaken enough to slow the acceleration? Could it eventually reverse? Could our prison walls eventually become penetrable? We do not know. The data is too preliminary. But it is a tantalizing possibility, one that future observations with DESI, the Euclid Space Telescope, and the Vera Rubin Observatory will help resolve. For now, though, the best available evidence still says our prison is permanent. The acceleration is real, ongoing, and shows no definitive signs of stopping. Let me now take you through the history of how this prison was built, because our universe was not always like this. There was a time when the prison did not exist, a time when, in principle, all parts of the universe were accessible to each other. And understanding how we went from that state to our current state of imprisonment is one of the great stories of modern physics. In the very earliest moments after the Big Bang, the universe was unimaginably small, hot, and dense. All the energy that would eventually become every galaxy, every star, every atom in the observable universe was concentrated in a region far smaller than a proton. The physics of this earliest instant is still poorly understood. We need a theory of quantum gravity to describe it, and we do not yet have one. But very shortly after the beginning, something extraordinary happened. A quantum field called the inflaton field entered a state of high energy. This high energy state had a peculiar property. Just like dark energy today, but enormously stronger, it caused space to expand at an exponential rate. This period is called cosmic inflation. It lasted for an incredibly tiny fraction of a second, somewhere around 10 to the power of negative 36 to 10 to the power of negative 32 seconds. But during that fleeting instant, the universe expanded by a factor of at least 10 to the power of 26. That is a 10 followed by 26 zeros. The universe went from being smaller than a proton to being potentially larger than the currently observable universe in a fraction of a second, so small that no human language has a word for it. This is when our prison was built. Before inflation, the region that would become our observable universe was tiny enough that all parts of it could communicate with each other. Light could travel from one side to the other. Everything was causally connected. But inflation flung these regions so far apart, so rapidly, that they lost causal contact with each other. They could no longer communicate. They became separate bubbles, each destined to become an observable universe for any observers that might eventually evolve within it. Our observable universe is just one of these bubbles. Others exist, presumably, far beyond our horizon. But they are forever inaccessible. Inflation built the prison. But then, for a while, the prison seemed like it might have an escape hatch. After inflation ended, the expansion of the universe continued, but it was decelerating. Matter and radiation dominated the energy budget of the cosmos, and their gravitational attraction was slowing the expansion down. During this era, the cosmic event horizon was actually getting farther away. Our accessible region was growing. The prison walls were retreating. Given enough time, more and more of the universe would become reachable. But then, about 5 to 6 billion years ago, something changed. The density of matter had been decreasing as space expanded. It was getting diluted, spread thinner and thinner. But dark energy, with its constant energy density, was not diluting. It stayed the same. And eventually, dark energy's density exceeded the density of matter. Dark energy became the dominant component of the universe. And when that happened, the expansion stopped decelerating and started accelerating. The cosmic event horizon stopped retreating and started advancing. Our accessible region stopped growing and started shrinking. The prison door slammed shut, and it will never open again. Not unless dark energy changes its behavior dramatically, which, as far as we currently know, it will not. This transition from deceleration to acceleration happened about 5 billion years ago. We are currently about 8 billion years into the dark energy-dominated era. And unless something fundamentally changes about the nature of dark energy, this era will last forever. The acceleration will continue forever. Our prison will remain forever. We are in the final age of cosmic accessibility. From now on, things only get worse. Let us now explore exactly how things get worse. Let us trace the future of our cosmic prison across vast stretches of time. Right now, in the present day, we can observe about 2 trillion galaxies within our observable universe. We can theoretically send signals to objects within our cosmic event horizon at 16 to 17 billion light-years moving distance. The universe is rich, full, teeming with structure and light. Fast forward 100 billion years. The expansion has continued accelerating for roughly 90 billion more years. Most of the galaxies we can currently see have crossed our cosmic event horizon. Their light is still reaching us, but it is enormously redshifted, stretched to radio wavelengths or beyond. The universe visible to us is darker, emptier, lonelier. Our own galaxy, the Milky Way, has long since merged with the Andromeda Galaxy, our nearest large neighbor. This merger will happen in about 4 to 5 billion years. By 100 billion years, our local group of galaxies, about 54 galaxies bound together by mutual gravity, will have merged into a single giant elliptical galaxy. Let us call it Milkomeda, the name some astronomers have proposed. This single merged galaxy will be the only thing visible. Everything else will have been stretched beyond detection. An astronomer living in Milkomeda in 100 billion years, looking out at the sky with the most powerful telescope conceivable, will see nothing. No other galaxies, no cosmic web, no clusters or filaments, just their own galaxy, alone in an infinite, empty, black void. Now fast forward to 1 trillion years, 1,000 billion years. The situation is even more extreme. Not only are no other galaxies visible, but the cosmic microwave background radiation, the afterglow of the Big Bang itself, has been stretched to such long wavelengths that it is completely undetectable by any conceivable instrument. The evidence that a Big Bang ever happened is gone. The evidence that other galaxies ever existed is gone. The evidence that the universe is expanding is gone, because there is nothing visible to measure recession velocities from. Think about what this means. A civilization arising in this distant future will have no way of knowing that the Big Bang happened. They will have no way of knowing other galaxies exist. They will have no way of knowing the universe is expanding. They will look at their single galaxy, alone in a void, and they will conclude that this is all there is. The universe, to them, is one galaxy in infinite empty space. Static, eternal, alone, every major cosmological discovery of the 20th and 21st centuries. Everything from Hubble's expansion to the cosmic microwave background to dark energy itself, all of this will be undiscoverable to them. The evidence will have been erased by the expansion. The universe will have censored its own history. It will have deleted the records of its own birth. The prison will have not only trapped its inmates, but also burned the archives that showed there was ever anything outside the walls. We are living in a privileged epoch. Right now, today, in this era of cosmic history, we can still see the evidence. We can still detect the cosmic microwave background. We can still observe distant galaxies. We can still measure the expansion. We can still piece together the story of the universe's origin and fate. This will not always be the case. We are witnesses to cosmic history in a way that future civilizations never will be. And that is both a privilege and a responsibility. Now let us continue even farther into the future. 100 trillion years from now. By this time, the last stars have died. Stars like our Sun have lifespans of about 10 billion years. Red dwarf stars, the most common type, can burn for trillions of years. But even they eventually exhaust their hydrogen fuel and fade. By 100 trillion years, the era of starlight is over. The universe is dark. No nuclear fusion, no stellar radiation, just cooling remnants. White dwarfs fading to black. Neutron stars cooling. Black holes drifting. And beyond even this, on timescales of 10 to the power of 67 years and beyond, even protons may decay. The very atoms that make up matter might be unstable on sufficiently long timescales. Matter itself dissolves. What remains are black holes, which themselves evaporate through Hawking radiation over timescales of 10 to the power of 100 years for a supermassive black hole. And after the last black hole has evaporated, nothing. A thin gas of photons and leptons, eternally cooling, eternally diluting in an ever-expanding space. Maximum entropy. No gradients. No structure. No complexity. No information processing. No life. No thought. No observation. The prison is not just inescapable, it is eventually empty. A cell with nothing in it. For eternity. This is the heat death of the universe, and it is the final, ultimate expression of our cosmic imprisonment. Not only can we not escape the observable universe, but eventually, there will be nothing within it worth experiencing. The prison is eternal and will eventually become void. But let us pull back from this bleak far future. Let us return to the present and ask the most important question. Can we escape? Is there any possible way out? Any loophole in the laws of physics that might allow us or our descendants to break free of this cosmic prison? Let us examine every possible escape route with rigorous scientific honesty. Escape attempt number 1. Travel at the speed of light. The fastest possible speed. If we could somehow accelerate a spacecraft to the speed of light, could we escape the observable universe? No, absolutely not. Even at the speed of light, you can only reach objects within the cosmic event horizon. And reaching objects at the event horizon would require infinite time. Objects beyond the event horizon are fundamentally unreachable at light speed. The expansion of space between you and your destination creates new distance faster than you can cover it. You would be running on a treadmill set to a speed faster than yours. You would run forever and never advance. Moreover, no massive object can actually reach the speed of light. Special relativity tells us that as an object accelerates toward light speed, its mass effectively increases, requiring more and more energy to accelerate further. The energy required to reach light speed is infinite, so even reaching the maximum possible speed is impossible for anything with mass. We are doubly trapped. We cannot reach light speed, and even light speed is not fast enough. Escape attempt number 2. The Alcubierre warp drive. In 1994, Mexican physicist Miguel Alcubierre published a remarkable paper. He showed that Einstein's general relativity, the same theory that describes the expansion of the universe, also allows for a different kind of superluminal travel, not traveling through space faster than light, but warping space itself so that you arrive at your destination without ever locally exceeding light speed. The concept is elegant. You create a bubble of flat spacetime around your ship. In front of the bubble, you contract space. Behind the bubble, you expand space. The bubble, and everything inside it, is carried forward by the contraction of space ahead and the expansion of space behind. Inside the bubble, you are stationary. You feel no acceleration, no time dilation. You are just sitting in flat space. But the bubble itself can move at any speed, including faster than light. Because, just as with cosmic expansion, there is no limit to how fast space can be warped. This sounds like the perfect prison break. If we can warp space around us to move faster than the expansion, we could outrun the cosmic horizon. We could reach the unreachable. We could escape. But there is a devastating problem. Several, in fact. First, the Alcubierre drive requires exotic matter with negative energy density, not negative pressure, which dark energy has. Negative energy density. This is a fundamentally different thing. Negative energy density means less energy than the vacuum, which is defined as zero. This is not known to exist in classical physics. In quantum mechanics, there are certain configurations that produce negative energy densities, like the Casimir effect between conducting plates. But these are tiny, localized effects. The Alcubierre drive, in its original formulation, requires a total negative energy on the order of the mass energy of the entire observable universe. That is approximately 10 to the power of 53 kilograms converted to energy. This is clearly absurd. More energy than exists in everything we can see. Part 2 subsequent work by physicists like Chris van den Broek and Harold White has reduced the energy requirements dramatically by modifying the geometry of the warp bubble. But even the reduced requirements are still far beyond anything achievable with known physics. And the fundamental problem of requiring negative energy density remains unsolved. Second, even if we could create a warp bubble, there are serious problems with how you would actually start it, stop it, and control it. The geometry requires the warp bubble to already be traveling in order for it to be created. You cannot create one from rest and then accelerate it. There are also issues with the accumulation of high-energy particles on the bubble wall during travel, which would be released as a lethal burst of radiation upon arrival. Third, and perhaps most importantly, several analyses suggest that the Alcubierre drive violates causality. It allows the creation of closed time-like curves, essentially time travel into the past. Most physicists believe that nature has some mechanism, a chronology protection conjecture as Stephen Hawking called it, that prevents such violations. If this is true, then the Alcubierre drive is not merely difficult, but physically impossible. So the warp drive remains an interesting mathematical solution within general relativity, but almost certainly not a practical escape route from our cosmic prison. Escape attempt number 3. Wormholes. Another solution within general relativity that could potentially allow faster than light travel. A wormhole, also called an Einstein-Rosen bridge, is a hypothetical tunnel through space-time connecting two distant points. Instead of traveling through the vast expanse of space between two locations, you simply step through the wormhole and emerge at the other end instantaneously. Wormholes are mathematically valid solutions to Einstein's field equations. They were first described by Einstein and Rosen in 1935, and they represent, in principle, the ultimate prison break. If you could create a wormhole with one end inside the observable universe and the other end beyond the cosmic event horizon, you could step through and escape. But the problems with wormholes are even more severe than those with warp drives. First, we have no evidence that wormholes exist naturally anywhere in the universe. They are mathematical possibilities, not observed realities. Second, any wormhole that did form would be unstable. It would collapse into a singularity, like a black hole, before anything could pass through. The walls of the wormhole would close in at the speed of light, destroying anything inside. To keep a wormhole open and traversable, you again need exotic matter with negative energy density. Same problem as the warp drive. The throat of the wormhole must be threaded with negative energy to prevent collapse. And the amounts required are enormous. Third, just like the warp drive, a traversable wormhole connecting two points can potentially be used to create closed, time-like curves. Time travel. And the same chronology protection considerations apply. Nature likely forbids it. Fourth, even if you could create a stable, traversable wormhole, you would need to somehow get one end of it beyond the cosmic event horizon in the first place. But getting anything beyond the event horizon is precisely what we are trying to do and cannot do. It is a circular problem. To escape the prison, you need a wormhole that exits beyond the wall. But to get one end of the wormhole beyond the wall, you need to have already escaped. It is a catch-22. Escape attempt number 4. Quantum entanglement. This is one of the most commonly cited misconceptions about potential faster-than-light communication or travel. Quantum entanglement is a real physical phenomenon. When two particles are entangled, measuring a property of one instantly determines the corresponding property of the other, regardless of the distance between them. Einstein called it spooky action at a distance. And it seems, on the surface, like it could allow faster-than-light communication. If I can instantly affect a particle on the other side of the universe just by measuring its partner here, surely I can use this to send a message faster than light? No, you cannot. This is one of the most firmly established results in quantum information theory. It is called the no-communication theorem. While entanglement correlations are real and instantaneous, they cannot be used to transmit information. The reason is subtle, but absolute. When you measure your entangled particle, you get a random result. You cannot choose what result you get. You cannot encode a message in the outcome, because you have no control over what the outcome will be. The correlations only become apparent when you compare results with your distant partner, and that comparison requires a classical communication channel which is limited to the speed of light. So entanglement, as exotic and counterintuitive as it is, cannot help us escape our cosmic prison. It cannot carry information faster than light. It cannot break the speed limit. It is not a communication channel. It is a correlation, nothing more. Escape attempt number 5. Can we wait for dark energy to weaken or reverse? This is the only escape route that is not ruled out by fundamental physics. If dark energy is not constant, if it is dynamic and evolving, then it is at least conceivable that it could weaken over time. If it weakened enough, the acceleration would stop. The cosmic event horizon would retreat. Our accessible region would grow again. In the most optimistic scenario, dark energy could reverse sign entirely, becoming attractive rather than repulsive, leading to a deceleration and eventual recollapse of the universe. as I mentioned earlier. The DESI Collaboration's 2024 results hint that dark energy might not be perfectly constant, but the hints are weak and the uncertainties are large. And even if dark energy is weakening, there is no guarantee it will weaken enough or reverse. It might asymptotically approach some small positive value. It might oscillate. We simply do not know. Moreover, even if dark energy eventually reverses, the objects that have already crossed our cosmic event horizon are gone forever. The information they carried, the light they emitted, the civilizations they might have hosted, all of it has passed beyond the point of no return. Even if the prison gates eventually open, the prisoners who already escaped beyond the walls are lost. We can never retrieve what has already been taken from us, and the timescales involved, even in the most optimistic scenarios, are hundreds of billions of years at minimum. Far longer than the remaining lifetime of our sun, our solar system, or even our galaxy in its current form. Escape attempt number 6. Sending information rather than traveling physically. Maybe we cannot escape the prison in person. But can we send a message? Can we transmit information to civilizations beyond the horizon? For objects that have not yet crossed the cosmic event horizon, yes, we can, in principle, send them signals. Light, radio waves, gravitational waves. Those signals will eventually reach them, though they will be redshifted and attenuated by the expansion of space. But for objects already beyond the event horizon, no signal we send, no matter how powerful, no matter how focused, no matter what form it takes, will ever reach them. The signal travels at the speed of light at best, and at their distance, the expansion of space creates new distance faster than the signal can cover. The message runs forever and never arrives. It is like writing a letter and throwing it into a river that flows faster than your throw. The letter falls short, always, no matter how hard you throw. And even for objects still within the event horizon, time is limited. As the expansion accelerates, objects near the event horizon are approaching it. Signals sent to them must be sent now, while they are still reachable. Every moment we wait, the set of reachable objects shrinks. Delay is permanent loss. So what is the verdict? After examining every conceivable escape route with rigorous scientific analysis, the conclusion is clear and unavoidable. There is no known way to escape the observable universe's causal boundary. The cosmic event horizon is an absolute, fundamental barrier imposed by the geometry of space-time and the nature of dark energy. It is not a technological limitation that more advanced civilizations might overcome. It is not a challenge waiting for a sufficiently clever solution. It is a consequence of the deepest laws of physics we know. Breaking it would require violating causality, the speed of light, or the fundamental principles of general relativity. And there is no evidence, theoretical or experimental, that any of these can be violated. We are prisoners. Permanently, inescapably, the universe has placed an absolute limit on our reach, our knowledge, and our influence. And dark energy ensures that this limit only grows more restrictive with time. But now let us shift our perspective. Let us bring quantum physics into this discussion and see what it adds to our understanding of this cosmic prison. Because quantum mechanics, the physics of the very small, has a surprising amount to say about the physics of the very large. One of the most remarkable connections between quantum physics and our cosmic prison involves the origin of the prison itself. Remember inflation, the brief period of exponential expansion in the first fraction of a second after the Big Bang. The period that built our prison by stretching space so dramatically that most of it ended up beyond our horizon. What drove inflation? A quantum field, the inflaton field. And what determined the structure of everything we see today? Quantum fluctuations in that field. During inflation, quantum mechanical uncertainty meant that the inflaton field's value was not perfectly uniform. It had tiny random variations from point to point, governed by the Heisenberg uncertainty principle. These variations were incredibly small, fluctuations of about 1 part in 100,000. But inflation took these microscopic quantum fluctuations and stretched them to cosmic scales. Those tiny random variations became the seeds of all structure in the universe. They became the slight density variations that gravity later amplified into galaxies, clusters, filaments, voids, and everything else. So here is the profound realization. The same quantum physics that governs the behavior of subatomic particles is responsible for the large-scale structure of the cosmos. The same uncertainty principle that prevents you from knowing both the position and momentum of an electron simultaneously is what created the pattern of galaxies across the sky. And the same inflationary mechanism that turned these quantum seeds into cosmic structure is what stretched the universe so large that most of it ended up beyond our horizon. Quantum mechanics built our prison. The very same physics that makes atoms work, that allows chemistry and biology and consciousness to exist, is the same physics that inflated space to incomprehensible vastness and created the cosmic horizon that traps us. Our existence and our imprisonment have the same origin. They are two sides of the same quantum coin. There is another deep connection between quantum physics and cosmic horizons that is worth exploring. It involves Hawking radiation, one of Stephen Hawking's most famous theoretical discoveries. In 1974, Hawking showed that black holes are not perfectly black. They emit radiation. Very slowly, very faintly, but they emit. This radiation arises because of quantum effects near the event horizon of the black hole. In quantum field theory, the vacuum is not empty but full of virtual particle-antiparticle pairs constantly popping into existence and annihilating each other. Near a black hole's event horizon, one of these virtual particles can be captured by the black hole while the other escapes. The escaping particle carries away energy, which we observe as Hawking radiation. Over immense timescales, this radiation causes the black hole to lose mass and eventually evaporate completely. Now here is the connection to our cosmic prison. In 1977, physicists Gary Gibbons and Stephen Hawking showed that the same effect applies to the cosmic event horizon. Just as a black hole's event horizon emits Hawking radiation because of quantum effects at the boundary, the cosmic event horizon also emits radiation. This is called Gibbons-Hawking radiation or de Sitter radiation. It gives the cosmic horizon a temperature, just as Hawking radiation gives a black hole a temperature. The temperature of our cosmic event horizon is incredibly low, about 10 to the power of -30 Kelvin. That is incomprehensibly cold. Trillions of times colder than even the cosmic microwave background, which is itself only 2.7 Kelvin. We could never detect this radiation directly. But its existence is significant because it tells us something profound about the nature of our prison walls. The cosmic event horizon is not just a geometric abstraction. It has physical properties. It has a temperature. It has an associated entropy related to its area. It radiates. The walls of our prison are not just conceptual boundaries. They have a physical character. They affect the quantum vacuum. They interact with quantum fields. They are real in a deep physical sense. This connects to another deep idea in theoretical physics called the holographic principle. Proposed by Gerard 't Hooft and Leonard Susskind in the 1990s, the holographic principle states that all the information contained within a region of space can be encoded on the boundary of that region. Like a hologram, where a two-dimensional surface contains all the information needed to reconstruct a three-dimensional image, the boundary of a region of space contains all the information about what is inside. Applied to our cosmic prison, this suggests something remarkable. All the information about everything within our observable universe, every particle, every interaction, every event, could in principle be encoded on the cosmic event horizon itself. The wall of our prison contains the complete description of everything inside it. We are, in a sense, a holographic projection from the boundary. This is speculative and not fully understood. The holographic principle is best established in the context of anti-de Sitter space, a different geometry from our actual universe. Extending it to our de Sitter-like universe with a cosmological constant is an active area of research, but if it holds, it adds yet another layer to the nature of our cosmic imprisonment. We are not just contained by the horizon, we might be the horizon, in some deep informational sense. Let us also consider what quantum gravity, the yet-to-be-completed unification of quantum mechanics and general relativity, might say about our prison. Currently, our best theory of gravity is Einstein's general relativity, and our best theory of the quantum world is quantum field theory. Both work extraordinarily well in their respective domains, but they are fundamentally incompatible. General relativity describes space-time as smooth and continuous. Quantum mechanics suggests that at the smallest scales, everything is discrete and quantized. To fully understand the cosmic horizon, especially its quantum properties like Gibbons-Hawking radiation and its holographic nature, we likely need a complete theory of quantum gravity. Several candidate theories exist. String theory proposes that the fundamental constituents of nature are tiny one-dimensional strings vibrating at different frequencies. Loop quantum gravity proposes that space-time itself is quantized, made up of discrete units at the Planck scale of about 10 to the power of -35 meters. Other approaches exist as well. Some of these theories suggest that space-time might be emergent rather than fundamental. That is, space and time as we experience them might not be the deepest level of reality. They might arise from something more fundamental, perhaps from quantum entanglement patterns, as some approaches suggest, or from some pre-geometric structure. If space-time is emergent, then our cosmic prison, which is a feature of space-time geometry, might also be emergent. It might be a description-dependent feature rather than an absolute one. At the deepest level of reality, the notion of being separated by distance might not even apply. Objects beyond our cosmic horizon might not be truly separated from us in whatever fundamental framework underlies space-time. This is highly speculative. We do not have a complete theory of quantum gravity. We do not know if space-time is emergent. And even if it is, we have no mechanism for exploiting this to escape our cosmic prison in any practical sense. But it is worth noting that the prison might be a feature of our description of reality rather than of reality itself. One particularly intriguing conjecture in this regard is the ER equals EPA proposal by Juan Maldacena and Leonard Susskind from 2013. ER refers to Einstein-Rosen bridges, which are wormholes. EPA refers to Einstein-Podolsky-Rosen correlations, which is entanglement. The conjecture states that these two seemingly different phenomena are actually the same thing. Every pair of entangled particles is connected by a microscopic wormhole, and every wormhole is a manifestation of entanglement between the quantum states on either side. If this conjecture is correct, then entanglement and wormholes are the same physical phenomenon described in different languages. And since entanglement can exist between particles separated by the cosmic event horizon, there might be some sense in which quantum connections persist across the horizon, even though classical communication does not. But again, the no communication theorem still applies. These quantum connections cannot be used to transmit information. The prison remains unbreachable for any practical purpose. The ER equals EPRA conjecture does not offer an escape route. It offers a deeper understanding of why the prism works the way it does. Now let us turn to what is perhaps the most philosophically disturbing aspect of our cosmic imprisonment: the implications for knowledge and for any intelligent civilization that might exist in the universe. We discussed earlier that future civilizations will lose access to the evidence for the Big Bang and for the existence of other galaxies. But let us think more carefully about what this means for the enterprise of science itself. Science works by observing the universe, forming hypotheses, and testing them against data. But what happens when the data disappears? What happens when the evidence is systematically erased by the expansion of space? Future civilizations will not just be ignorant of the Big Bang. They will be unable to discover it. They will not be lazy or unintelligent. The evidence will simply not exist for them. The photons that carry the information will have been stretched to wavelengths longer than their observable universe. The distant galaxies whose recession proves expansion will have vanished. The cosmic microwave background that confirms the hot early universe will be undetectable. These civilizations will do science as rigorously as we do. They will look at the available evidence. They will form the best models that explain their observations. And their models will be wrong. They will conclude they live in a static universe containing a single galaxy. They will have no reason to think otherwise. Every observable fact will be consistent with this incorrect conclusion. Their science will be correct given their data. But their data will be incomplete. The universe will have hidden the truth from them. This raises a terrifying epistemological question. If this can happen to future civilizations, could it be happening to us right now? Could there be evidence, cosmic information that was once accessible but has already passed beyond our horizon, that we have already lost? Could our current understanding of the universe be incomplete, not because we lack the intelligence or technology to understand it, but because the relevant evidence has been physically removed from our accessible universe? In principle, yes, if important physical processes happened primarily in regions that have since crossed our event horizon, or if evidence existed in the early universe that has since been diluted beyond detection, then we might be missing crucial pieces of the puzzle. We have no way to know what we do not know. We can only work with the evidence available. And the evidence available is fundamentally limited by the cosmic horizon. This is not just a practical limitation like needing a bigger telescope. This is a fundamental epistemological limit imposed by the geometry of space-time. There exist true facts about the universe that we can never confirm or even access data about. Our knowledge has a ceiling, not a ceiling of intelligence or effort or technology, but a ceiling of physics. Now let us discuss another aspect of our cosmic imprisonment that is often overlooked: the loneliness implication. If intelligent life exists elsewhere in the universe, and given the hundreds of billions of galaxies, each containing hundreds of billions of stars and likely trillions of planets, it seems statistically very likely that it does, then most of that intelligent life is beyond our cosmic event horizon. We can never detect it. We can never communicate with it. We can never know of its existence through any direct means. Imagine a universe teeming with billions of intelligent civilizations, each one advanced, each one curious, each one looking up at their sky, wondering if they are alone, and each one trapped within their own cosmic event horizon, unable to communicate with any of the others. Each one an island of intelligence in an infinite ocean of expanding emptiness. Each one asking the same question: is anyone out there? And never receiving an answer. Not because the answer is no, but because the prison walls prevent the answer from ever arriving. Even within our own observable universe, the situation is grim for interstellar communication over cosmic timescales. Galaxies that we can currently see are crossing the event horizon as we speak. If intelligent civilizations exist in those galaxies, they are becoming unreachable right now. We are losing potential cosmic neighbors every second. Every second of delay in making contact with distant civilizations is a second in which some of them become permanently unreachable. There is a poignant urgency hidden in this physics. If we ever want to communicate with other intelligences in the cosmos, there is a window. That window is open now. But it is closing. Not rapidly by human standards, but inexorably by cosmic ones. Every moment we wait, the universe beyond our reach grows larger, and the universe within our reach grows smaller. Let us now address the mathematics that underlies all of this more carefully. Because while I have been explaining these concepts in words and analogies, the actual physics is mathematical. And the mathematics is what makes the conclusions unavoidable. The expansion of the universe is governed by the Friedmann equations, derived from Einstein's general theory of relativity applied to a homogeneous, isotropic universe. These equations relate the expansion rate to the energy content of the universe. The key quantity is the scale factor, usually written as a of t. This is a number that describes how distances in the universe change over time. If a doubles, then all distances between widely separated objects double. Today, by convention, we set A equals 1. In the past, A was less than 1. In the future, A will be greater than 1. The first Friedmann equation tells us how fast the scale factor changes. It says that the rate of expansion depends on the total energy density, matter, radiation, and dark energy. Matter's energy density dilutes as the cube of the scale factor. As space expands, matter spreads out. Radiation dilutes as the fourth power of the scale factor. It spreads out and also loses energy due to redshift. But dark energy, if it is a cosmological constant, does not dilute at all. Its energy density stays the same, regardless of how much the universe expands. In the early universe, when the scale factor was small, matter and radiation were dense and dominated the energy budget. Their gravitational attraction slowed the expansion. But as the universe expanded and matter and radiation diluted, dark energy's constant density eventually became dominant. Once dark energy dominates, the expansion accelerates exponentially. The scale factor grows as an exponential function of time. This is called de Sitter expansion. After the Dutch astronomer Willem de Sitter, who first described such a universe in 1917. In a de Sitter universe with exponential expansion, the cosmic event horizon has a fixed proper distance. It is given by the speed of light divided by the Hubble parameter of the de Sitter phase. Numerically, this gives us the approximately 16 to 17 billion light-year event horizon we have been discussing. The mathematical proof of our imprisonment comes from a specific integral. The comoving distance that a light signal emitted today can ultimately reach, given infinite time, is the integral from now to infinity of the speed of light divided by the scale factor. With respect to time. In a universe where the scale factor grows exponentially, this integral converges to a finite value. That is the key mathematical fact. The integral is finite. Even with infinite time, light can only cover a finite comoving distance. That finite distance is the event horizon. Beyond it, impossible. No matter how long you wait, the mathematics is absolute. For comparison, in a universe without dark energy, where the expansion decelerates, the scale factor grows as a power law rather than an exponential. In that case, the integral diverges. It is infinite. Meaning, given enough time, light can reach any point. There is no event horizon, no prism. The expansion slows enough that light can always eventually catch up. Dark energy, by making the expansion exponential, is what converts a universe with no event horizon into a universe with one. It is what creates the prism. Without dark energy, we would be free. With it, we are trapped. It really is that simple mathematically. The cosmological constant creates a finite event horizon. And a finite event horizon means permanent, absolute imprisonment. Let us now talk about something that connects all of these ideas together: the concept of the Hubble tension and what it means for our understanding of the prison. The Hubble constant, as I mentioned earlier, measures the current rate of expansion. But there is a problem. Two different methods of measuring it give different answers. If you measure it from the cosmic microwave background radiation, using the physics of the early universe extrapolated to today, you get a value of about 67.4 kilometers per second per megaparsec. This is the value from the Planck satellite collaboration. But if you measure it from the local universe, using nearby supernovae and Cepheid variable stars as distance ladders, you get a value of about 73 kilometers per second per megaparsec. This is the value from the Shuri-S collaboration led by Adam Riess. The difference between these two measurements is about 8%. That might not sound like a lot, but the measurements are each so precise that the difference is statistically very significant. At least 4 to 6 sigma, depending on which data sets you use. This means the probability that the discrepancy is due to random chance is less than 1 in a million. This is called the Hubble tension, and it is one of the biggest unsolved problems in cosmology today. Either one or both measurements have an unidentified systematic error, which is possible but which extensive investigation has not revealed. Or the standard model of cosmology is wrong in some way. And if the standard model is wrong, it could affect our understanding of dark energy, the expansion history, and ultimately the nature and permanence of our cosmic prison. Various proposed solutions to the Hubble tension include early dark energy, an extra burst of dark energy in the early universe that affects the CMB measurement, or new physics in the neutrino sector, or time-varying dark energy, or interactions between dark matter and dark energy. Each of these proposals, if correct, would modify our understanding of the expansion history and potentially affect the event horizon calculation. But none of them eliminate the event horizon. As long as the expansion is accelerating, regardless of the exact rate, an event horizon exists. The Hubble tension affects the precise size of our prison, but not the fact that we are in one. The prison remains, whatever the resolution of this puzzle turns out to be. Now, let us discuss the relationship between black holes and our cosmic prison, because this connection illuminates something deep about the nature of horizons in physics. A black hole has an event horizon. It is a surface in space from which nothing, not even light, can escape. Once you cross the event horizon of a black hole, you are trapped inside forever. You will inevitably fall toward the singularity at the center. No force in the universe can prevent this. The event horizon is an absolute one-way membrane. Things can fall in, nothing can come out. Our cosmic event horizon is similar in many ways. It is also a surface beyond which signals cannot reach us. It is also a one-way boundary. Signals from beyond the cosmic event horizon can never reach us, just as signals from inside a black hole can never reach the outside. There are, of course, differences. With a black hole, the horizon traps things inside a small region. With the cosmic horizon, it traps us inside a vast region, while the rest of the universe is outside. And with a black hole, the trapped objects are inevitably destroyed at the singularity. With the cosmic horizon, the trapped observers are not destroyed. We just cannot leave. But the mathematical structure is remarkably similar. Both horizons emit Hawking radiation. Both have temperatures. Both have associated entropies. Both represent fundamental causal boundaries. And both arise from the same underlying physics, general relativity, and the structure of spacetime. In fact, there is a beautiful mathematical duality between a black hole event horizon and a cosmic event horizon. In both cases, the horizon defines the boundary between accessible and inaccessible regions. In both cases, quantum effects create radiation at the boundary. And in both cases, the information content of the region is bounded by the area of the horizon. In accordance with the holographic principle, this duality suggests that our cosmic prison and a black hole prison are in some deep theoretical sense the same kind of phenomenon viewed from different perspectives. We are inside our cosmic horizon, looking out at an unreachable exterior. An observer falling into a black hole is outside the black hole horizon, looking at an unreachable interior. Both are permanently separated from a region of spacetime by a causal boundary. Let me now bring up a concept that is often misunderstood but is crucial for a complete picture of our cosmic prison. The concept of the particle horizon versus the event horizon. I mentioned both earlier, but let us be very clear about the distinction because it is critical. The particle horizon is the boundary of the observable universe. It represents the maximum distance from which light has had time to reach us since the Big Bang. It is determined by looking backward in time. How far could a photon have traveled in the entire age of the universe? The answer gives us the particle horizon, currently at 46.1 billion light-years moving distance. The event horizon is different. It represents the maximum distance to which we can send a signal that will ever be received, looking forward in time. How far can a photon emitted today travel in all of future time? With accelerating expansion, the answer is finite, about 16 to 17 billion light-years moving distance. The crucial and disturbing fact is that the event horizon is inside the particle horizon. The boundary of what we can reach is smaller than the boundary of what we can see. There is a shell of the universe that we can observe, but never influence. We can see galaxies there, we can study their light, we can learn about them. But we can never visit them, never send them a message, never affect them in any way. They are ghosts. Visible but untouchable, knowable but unreachable. And this shell is growing. As the expansion accelerates, more and more of the observable universe transitions from reachable to unreachable. The event horizon shrinks relative to the particle horizon. Our sphere of influence shrinks while our sphere of observation grows. We see more and more of the universe's past while being able to affect less and less of its future. This is perhaps the cruelest aspect of our cosmic prison. It is not that we are denied knowledge. We can observe almost everything. It is that we are denied agency. We can see what exists, but cannot interact with it. We are cosmic voyeurs, watching a universe unfold that we can never participate in beyond our shrinking bubble. Let me now turn to discussing the large-scale structure of the universe within our prison, because understanding what is inside our accessible region tells us something about what we can still do within our constraints. The observable universe is not uniform. It has structure. Magnificent, intricate, beautiful structure. Galaxies are not scattered randomly. They are organized into a vast cosmic web. Imagine a three-dimensional network of filaments and walls surrounding enormous empty voids. At the intersections of filaments are clusters of galaxies, the largest gravitationally bound structures in the universe. Along the filaments are chains of galaxies, and in between, vast empty regions called voids, some hundreds of millions of light-years across containing almost nothing. This cosmic web was seeded by those quantum fluctuations during inflation that I discussed earlier. The slight density variations, 1 part in 100,000, grew over billions of years under the influence of gravity into the large-scale structure we see today. Dense regions attracted more matter and became denser. Underdense regions lost matter and became emptier. Through gravitational instability, the subtle quantum signal was amplified into a cosmic symphony of structure. Within our observable universe, we have mapped this structure to considerable detail. Surveys like the Sloan Digital Sky Survey have measured the positions and distances of millions of galaxies, revealing the cosmic web in stunning detail. And future surveys like those from DESI and the Vera Rubin Observatory will map it with even greater precision. But here is the important point. Gravity works differently from the cosmic expansion. While the expansion stretches space everywhere, gravity can overpower the expansion locally. In regions where matter is concentrated enough, gravity pulls things together despite the expansion trying to pull them apart. These gravitationally bound structures will remain together even as the expansion accelerates. They will not be torn apart by dark energy. So what remains gravitationally bound to us? What constitutes our permanent accessible universe, the part of the prison that will never be taken away? The answer is our local group. The Milky Way, the Andromeda Galaxy, the Triangulum Galaxy, and about 50 smaller dwarf galaxies. These are bound together by gravity into a structure about 10 million light-years across. The gravitational pull between these galaxies is strong enough to overcome the cosmic expansion. They will remain together indefinitely. Everything else, every other galaxy, every other cluster, every other structure, will eventually be carried beyond our event horizon by the accelerating expansion. In about 4 to 5 billion years, the Milky Way and Andromeda will collide and merge. Over the next several billion years, the other members of the local group will fall in as well, creating a single large galaxy. This merged galaxy will be our permanent home, our prison within a prison, a single galaxy in an otherwise empty observable universe. Let us now address an alternative fate for the universe that is worth discussing. The Big Rip. This is a hypothetical scenario in which dark energy is not merely constant, but actually increases in density over time. This type of dark energy is called phantom energy, and it has an equation of state parameter less than -1. In the standard cosmological constant model, dark energy has an equation of state parameter of exactly -1. This means its energy density stays exactly constant as space expands. The expansion accelerates, but gravitationally bound systems are stable. The local group stays together. Atoms stay together. The prison grows lonelier, but its inmates remain intact. But if dark energy has a parameter less than -1, things are much more extreme. In this phantom energy scenario, the energy density of dark energy actually increases over time. The repulsive force grows stronger and stronger. And eventually, it overwhelms everything, not just the expansion of distant galaxies. Everything, in a finite time, the expansion becomes so extreme that it tears apart galaxy clusters, then individual galaxies, then solar systems, then planets, then atoms, then atomic nuclei, then space-time itself. This is the Big Rip. The complete destruction of all structure in the universe. Current observations are consistent with the cosmological constant value of -1. They do not favor phantom energy, but they do not conclusively rule it out either. The uncertainty is small but non-zero. If phantom energy is real, then our prison is not just inescapable. It is eventually lethal. The walls do not just keep us in, they eventually close in and crush us. Everything we are made of would be ripped apart. However, most cosmologists consider the Big Rip unlikely based on current data. The standard cosmological constant scenario remains the best fit. So let us proceed with that as our baseline expectation. The prison is permanent. But its inmates survive. They just become increasingly isolated. I want to now discuss a subtle but important point about what it means for something to cross our cosmic event horizon. Because the crossing is not a sudden event from our perspective. It is a gradual fading. When a galaxy crosses our event horizon, it does not suddenly vanish from our view. Remember, we see the galaxy by its light. And light that was emitted before the galaxy crossed the horizon is still traveling toward us. It takes time to arrive. So after the galaxy crosses the horizon, we still see it for a while. We are seeing its past self, from before it crossed. But the light we receive from it becomes more and more redshifted. The expansion stretches its wavelengths longer and longer. Visible light shifts to infrared, then to microwave, then to radio wavelengths. Simultaneously, the rate at which photons arrive decreases. The galaxy appears to dim. From our perspective, it seems to slow down, redden, and fade. It asymptotically approaches a frozen, infinitely redshifted image. It never quite disappears from our mathematical description, but practically, it becomes undetectable in finite time. This is analogous to what happens when an object falls into a black hole, as seen by an external observer. The object appears to slow down, redshift, and freeze at the horizon. It never quite crosses from the external observer's perspective. But for all practical purposes, it is gone. So the galaxies that are crossing our cosmic event horizon right now will slowly fade from our view over the coming billions of years. Their light will stretch to undetectable wavelengths. Their images will freeze and dim, and eventually, they will be indistinguishable from empty space. The universe will darken, one galaxy at a time, until only our local group remains visible. This brings up an interesting practical question. How much of the universe that we can currently see will we eventually lose? The answer is almost all of it. Of the roughly 2 trillion galaxies in the observable universe, only about 54 in our local group are gravitationally bound to us. Everything else will eventually cross the event horizon and be lost. That means we will lose approximately 99.99997% of the galaxies we can currently observe. The universe we can see will go from 2 trillion galaxies to 54. From a rich, complex, interconnected cosmic web to a single isolated island. Let me now transition to discussing some of the deeper theoretical frameworks that might someday give us a better understanding of our cosmic prison. One of the most interesting developments in theoretical physics in recent decades is the ADS/CF correspondence, also known as the Maldacena conjecture, proposed by Juan Maldacena in 1997. This is a duality between a gravitational theory in a specific type of spacetime called anti-de Sitter space and a quantum field theory without gravity living on the boundary of that spacetime. Anti-de Sitter space is a spacetime with a negative cosmological constant. It naturally contracts rather than expands. It is very different from our universe, which has a positive cosmological constant and is expanding. But the ADS/CF correspondence has been enormously productive in understanding the relationship between gravity, quantum mechanics, and information. It provides a concrete realization of the holographic principle, showing explicitly how a higher dimensional gravitational theory can be exactly equivalent to a lower dimensional non-gravitational theory on the boundary. The question that many theoretical physicists are currently working on is whether something similar exists for de Sitter space, the space-time with a positive cosmological constant that approximates our actual universe. This is called the DS-CFT correspondence, and it is much less well understood. If it exists, it would tell us that our entire universe, everything within our cosmic horizon, is dual to some kind of theory living on the cosmic event horizon itself. What this would mean for our prison is profound. It would mean that the prison wall is not just a boundary that limits us. It is us, in some deep mathematical sense. The interior of the universe and the boundary would be two descriptions of the same thing. The prison and the prisoner would be one, and escaping would be as meaningless as trying to escape from yourself. This is extremely speculative and not established, but it represents the frontier of our thinking about what cosmic horizons really are. They might not be walls at all, in the deepest sense. They might be the very fabric from which our reality is woven. Another important theoretical consideration involves the concept of eternal inflation and the multiverse. According to some models of inflation, the inflationary process does not end everywhere at once. Instead, it ends in local patches, creating bubble universes while continuing in the space between those bubbles. Each bubble universe has its own Big Bang, its own expansion history, its own physical constants perhaps. This creates an infinite collection of bubble universes, a multiverse. If this picture is correct, our observable universe is not just a small part of one larger universe. It is one of an infinite number of separate bubble universes. Each bubble is permanently out of causal contact with every other. The space between bubbles is inflating so rapidly that signals between them can never arrive. Our cosmic prison is not just within our bubble. Our entire bubble is a prison within the larger multiverse. There are layers of imprisonment. We are trapped within our event horizon, within our observable universe, within our bubble universe, within an eternally inflating multiverse. Each layer is unbreachable. Of course, eternal inflation remains theoretical. We have no direct evidence for the multiverse. And some physicists question whether a multiverse model is even scientific, since it may be untestable. But it is a logical consequence of many well-motivated inflationary models. And if it is true, it means our imprisonment is even more profound than we have discussed. We are not just cut off from most of our own universe. We are cut off from most of reality. Let us now take a step back and think about what all of this means from the perspective of what we can do within our prison. Because while the cosmic event horizon limits our reach, what remains accessible to us is still staggeringly vast. Our local group of galaxies, the part that will remain gravitationally bound and accessible to us forever, contains hundreds of billions of stars. The Milky Way alone has between 100 billion and 400 billion stars. Andromeda has approximately 1 trillion. Each of these stars potentially hosts planetary systems. The number of planets in our accessible universe is likely in the trillions. The diversity of environments, from gas giants to rocky worlds to moons with subsurface oceans, is enormous. Even limited to our local group, a civilization with sufficiently advanced technology would have enough matter, energy, and complexity to sustain itself for timescales that dwarf the current age of the universe. The last red dwarf stars will burn for trillions of years, vastly longer than the 13.8 billion years since the Big Bang. Our prison may be limited in spatial extent, but it is generous in time and resources within those limits. Moreover, the physics within our prison is rich and complex. Quantum mechanics, general relativity, thermodynamics, chemistry, biology, all of it operates the same inside our horizon. We can still explore, discover, create, and understand. The cosmic event horizon limits our physical reach, but it does not limit the depth of our understanding or the richness of our experience. We can still explore the laws of physics themselves, which are presumably the same everywhere, inside and outside the horizon. Let me now discuss a concept that ties together several threads we have been exploring. The concept of cosmic information loss and what it means for physics.